Okay, let's get started. So hopefully all of you turned in the homework that was due last night, right? I issued another homework on Wednesday. It's due next Thursday, okay? After today, you should have everything you need to start that homework or actually complete that homework. Right now, you have most of it. I think 4 out of the 5 questions or 3 out of the 4 questions. I also set up another quiz for next week, but there is one that's this week, right? That's due by the end of the day tomorrow. Opened up yesterday. It's available till end of day tomorrow. I'm going to do everything I can to not, I'm going to do what I can, okay, to not issue any homework over spring break, okay? So hopefully you guys will be able to just crush out next week, finish a homework, finish a quiz, and then have a nice break for a week, okay? Any questions? None? Okay. We started stress concentrations on Wednesday. Can't believe it's Friday. The week just keeps going by fast. I talked about the St. Venant's principle, right? Just the concept that as you get further away from applied force, right, we get this uniform behavior as we get out into our member. We would see some stress concentrations at the point of load application, right? You have this discrete small area over which a larger load might be acting. So you're going to get some stress concentrations right there, but it quickly dissipates and we will quickly get a uniform stress distribution, which we assumed in a lot of our problems. But in reality, right, we have stress concentrations. We have to deal with the fact that we have to move stress around discontinuities or design components, right, where we have holes or notches. Okay, or shoulder fillets, we're changing the size of a member, okay? In this case, we round out our holes, as you'll see in our diagrams, right? As I mentioned, well, here we'll say stress redistribution, excuse me. And movement of stress creates additional normal and shear stresses. Oops. Right. So the fact that we're trying to move stress around something, in doing that, we end up getting shear stresses and normal stresses, additional ones, okay, that we need to take into account. Because we might, up to this date, we've been designing for this nice uniform stress out in the cross section, right? Okay, we might design our member for that, and it might be adequate for that. We might make sure that it's underneath the ultimate stress or the yield stress, depending on what we consider the failure stress. Right? But the second we drill a hole through that element, right, that analysis goes out the window, and now we're going to have higher stress concentrations around where that hole is, or a change in the dimensions of our plate, right, notches, holes, or shoulder fillets. And so lucky for us, right, we're not the first engineers, okay, but we're the same as them, and we're lazy, and so we get to use, in this class, we're going to be using a lot of these graphs that help us essentially see how these discontinuities, in this case notches, affect the stresses in our bar, right? So in this case, we're starting out with axial stress. So we have, right, so the texts have developed solutions for many different cases. So I'm going to give you guys a little bit of a taste for this, okay, over the next day or so. And what they have done is they've created these graphs that give us a concentration factor, stress concentration factor. It's called K. All right, and K, as you see over here, right, got these two equations here. K is really equal to our max stress over our nominal stress, right? Or the max stress is equal to K times our nominal stress. This one right here is what we have to be careful with, because these graphs and these pre-packaged solutions are all calibrated for a certain calculation for the nominal stress. Yeah?
Is this the same K as we've been using in the...
No.
Oh,
As columns,
yeah.
different K.
Okay.
The K in columns is what we would call our effective length factor, right? We talked about how in columns that K essentially adjusts the equation to represent the boundary conditions or the fixity of the column that we're analyzing, right? So a pin-pin case is like our neutral case. That's where K equals to 1. That's where the original equation was calibrated for. We start fixing both ends, right? Then that K gets reduced. If we have a cantilever, right, it's fixed at the bottom and free at the top for a column, right? Our K jumps up to 2, and so on and so forth. So yeah, the K factor there is different than this K factor. This K factor is saying, okay, if we have a notched bar, right? We're pulling on it and we've got a notched bar, maybe we have to get through something, okay? Or we want to connect something else to this. And we notch it, the actual stress within this bar, the maximum stress within this bar, is going to be our nominal stress times our factor K, right? Where K is our max stress divided by our nominal stress. What you have to be careful of is when you calculate that nominal stress, depending on the solutions, depending on the text that you use, is based on certain dimensions of this notch. And in our text, it uses the small dimensions of our cross-section. So our nominal stress that you'll calculate, right, we'll know either a notch radius and an overall dimension, or they might even give us just the dimension of the notch, right, what's left of the material. And the nominal stress is the load that's on this plate, right, divided by the area, that'd be our normal stress. And the area over which you're calculating it over is the smaller area, right, little d times t, right, the thickness of the plate. So that's just the big thing to be careful with here. All right, and in our case, for our text, it's calibrated for the net section, the smaller section of our discontinuity, right? You'll see with the holes, same thing. It's going to be calculating it based on the, right, so this is a flat bar. With a notch. Now when we look at the next one, this is a flat bar with a hole. Right. Again, if we look closer here, right, our nominal stress is based on the net section. We are taking the stress over the material that's left around this hole, right? Thickness times the large diameter minus the small diameter of this hole. So that's getting us really what's the width that's left over on this plate. And so we're going to calculate what's the stress over this little area. And then we're going to amplify that by K, right? We're going to move this sigma nominal over here. We're going to say sigma nominal times K is sigma max. So we're going to amplify that nominal stress. That's really the stress over the material that's left adjacent to the holes. Right? But the fact that we're moving this stress around this hole, it amplifies it. So we're actually going to go above that stress by a factor of K. And we can get that factor by using these graphs, right? So in this case, for a flat plate with a hole in it, that K factor, right, is a function of this ratio of how big is the hole that we're drilling versus the overall width of the plate. The last one here is for our shouldered fillets, all right, or flat bar with fillets. Whoops. Whoops. Really getting after it here. So flat bar. With fillets, right? Again, max stress, sigma max, equals K, our stress concentration, times our nominal stress calculated at the net section, right? Again, looking at this, we're calculating our nominal stress based on the smallest area of material, right? Once we have that, right, our max stress, right? Because sigma equals P over A, we can use that maximum stress to design the element, right? Any questions? Oh, yeah.
Can you explain more like how to find the K and then so leaving the graph to find K, correct?
Yes, you need to go in the graph. And I guess this next example here, we go through two different cases. We're going to go through shouldered fillet and a drilled hole. And then we're going to go through exactly what we do, right? So in this case, we had a steel plate. It's under a tension load, right? For some reason, some design reason, right? Maybe we're trying to pull some load out at this hole here, right? Maybe we're trying to squeeze through something, so we're going to reduce the area, or we don't want to use that much plate material. It's expensive, okay? So in this case, our part is 20 millimeters thick. It's made out of bronze, okay? They give us the yield stress of that bronze is 331 megapascals. And they want us to determine what's the maximum safe load P if we have a factor of safety of 2.5 with respect to the failure by yield of this plate, okay? What do we know? We know that we have a thickness, it's 20 millimeters. They also give us those dimensions of our shouldered fillet, right? They say it's 15 millimeter radius. They say that our net width is 60 millimeters, right? The smallest width, the net width is 60 millimeters. The overall width is 90 millimeters. And they also give us the diameter of the hole is 27 millimeters. So we can have all of the dimensional information about our bar. We also were given the material properties. We're saying that the yield stress was 331 megapascals, right? You could also get this if we went out to the text. I don't know if anyone has gone out there to Appendix D. Appendix D in the text gives a bunch of different material types and gives a bunch of different information about the material properties of those materials, okay? Well, they gave us all the dimensions, they gave us the allowable stress, and they're asking us for the load. Well, as we know, both the hole and the shouldered fillets, right, they create an issue with stress concentrations, right? Because we have a change in dimension of our material, we're amplifying the stress that's seen in that material. And so we're going to need to go through and look at, right, two locations. We're really just looking at our changes in dimensions. So we have two locations of interest. Whoops, two ends. And we have two locations of interest, so we're going to need to calculate both. There's not a real way to just look at this and say one's going to control over the other. Maybe if you did this every day, okay? So we're going to calculate both. And determine the limiting one, right? Similar to what you did in the homework with you had your pipe that was rotating and you had a limit of 5 degrees of rotation, right? Or a limit of our shear stress, and you had to pick which diameter, right, would limit that to one or the other. So if we start, I'm going to start at the fillets. Well, if we go back up to our fillets, right, diagram, there's quite a few things in this diagram that we need to know, right? We're trying to get a stress concentration factor K, right? So we need to know a place on the x-axis and a curve, right? So if we knew a place on the x-axis, we know a curve, we could go to the x-axis, run up to our curve, and then run over, and we'll get our stress concentration factor, right? So on our x-axis, we have this R over D ratio, right? The radius of our fillet divided by our small width of our cross-section of our plate, right? And then up here, we have this big D over little d ratio, right? What's the difference in widths of our plate as we go from the small width to the large width, right? So those are the two things we need to calculate. So I'm going to first calculate this D over D ratio, right? Big D over little d, they say we need that. That's our curve. Well, in this case, we have 90 millimeters over 60 millimeters, or 1.5. The other one we need, right, our x-axis, was our radius over the small small width d. So we have 15 over 60, or 0.25. So we have 0.25 and 1.5. Well, if we come back up here, we start at 0.25, right, way over here. And we want to use the 1.5 curve, right? These two guys here, this one, and this one. So we just merely start here. We run up to our red. So we got some sort of K factor, right? 0.25 and 1.5. So we're over there. I'm going to say we're at like 1.73, okay? Pretty close, right? If I said 1.7, close enough. Right, 1.73. Well, that means we get to use now our maximum stress equation, which equals K times our nominal stress. Right, now we have K. We need to figure out our nominal stress, or our nominal stress, right? If we go back up to our figure, we want to make sure that we're using the right equation. Nominal stress is the load divided by the area of the smallest dimension of our bar, or B, or little d, times the thickness. All right, so this is equal to P over dt. Right. Well, our max stress, that's the maximum stress we're going to see in our bar, right? Well, that's also what we would call our failure stress, right? Well, in this case, they told us we had a factor of safety of 2.5, right? So we're going to say that we have our failure stress. As we know, factor of safety is our failure stress divided by F sub S, gives us our allowable stress, right? So this is the stress, sigma max. This is the stress that we're going to see in our bar. And we know that we can't let that exceed the allowable stress, right? The stress that we're going to allow this material to reach. Might not be the failure stress, and it's not going to be that because we have imposed a factor of safety on it, right? We want to sleep at night. So we're going to take that yield stress that we called our failure stress, which we were told was 331 megapascals, right? We're going to plug that in there. We're going to divide it by 2.5, and that's where we're going to limit the maximum stress in this material to. So what does that mean? Well, that means we've got 132.4 megapascals. That equals sigma max. That equals P over 20 millimeters divided by 60 millimeters times our K factor we decided was 1.73. We get a P of 91.8. Well, let's just start with the whole thing. 91,838 newtons, right? Megapascals are newtons per millimeter squared. So you make sure we continue with our units. So we have 91.8 kilonewtons. Right? So if we took our bar, as shown, and we apply 91.8 kilonewtons on the end of this bar, the stresses that we're going to end up seeing around these shouldered fillets are going to be our yield stress divided by 2.5, right? Our allowable stress. Just going to hit our allowable stress. If we put 91 kips on this thing, or kilonewtons, sorry. But we're not done yet. We've got these holes, or this hole. So at the hole, right, if we go back up to our graph now with respect to the holes, our nominal stress now is the load in our bar divided by the net area of material that's left, right? The diameter, overall diameter minus the diameter of the hole, right? We have one curve, which is really nice. All we really need to calculate, right, is this D over D ratio, or the x-axis value. Then we can run up to the curve and pull off a K value. So we're just going to do that really quick. D over D, 27 millimeters was our diameter of our hole. The large dimension is 90 millimeters. We get 0.3 approximately. If we go to our graph, we're going to get a K equal to approximately 2.36. So go back up here. What did I say the D value was? 0.3. 0.3. I'm going to run up. I'm going to run over. All right, that's our K value. Pull that K value off. I said it was 2.36, my guess. Pretty close. Again, we have max stress equals K times the nominal stress, right? Nominal stress is P over T times big D minus little d, right? The material that's left. We know what sigma max is, right? That is our sigma yield over our 2.5, or our factor of safety. So we end up getting this equation. That's P all over 20 millimeters, 90 minus 27, that's our diameters, times 2.36, that's our K. Gives us 1.32, 132.4 megapascals. So this gives us a K, or a P, equal to 70,700 newtons, or 70.7 kilonewtons. So which one controls? The whole controls, right? If we started at 0 kilonewtons and we slowly ramped it up, right? When we got to 70 kilonewtons, we would exceed our allowable stress, right? It wouldn't fail because we put a factor of safety on it, right? You could actually load it up to 2.5 times 70.7 kilonewtons, and then it would finally yield around that hole. But we don't want that, so we put a factor of safety on it. So when you get to 70.7 kilonewtons, that would be reaching our allowable load. Any questions? Yeah?
So the equation you use for the nominal value will always be given out of the graph that you use?
Yeah, it's always attached to the figure or the analysis that they did. Because you could do the same approach where you provided a stress concentration factor but you could calculate this nominal stress, right, based on the like the larger of the dimensions, and some textbooks do that, and some solutions do that. I just want to make sure that when we're using our text does it based on the smaller dimensions. So just make sure you're looking on the graph and looking at what the nominal stress is calculated based on, and use the correct inputs to do that.
So for like a homework or like a quiz question, would the graph be attached to the question, or do we have to find it?
The graph would be attached to the question. Yeah. Well, like if you were sitting down in here and taking an assessment, if you're taking the quiz, right, you can use the textbook, and then you can look up this figure. So. Any other questions? No. All right. Well, as you can imagine, with axial, we have the exact same behavior that happens in torsional systems also. So similar to axial concentrations, but now we're dealing with shear stresses, right, instead of axial stresses. And in this case, we have tau max equals K times tau nominal, right? If we looked at that equation right there, if we took tau nominal, we moved it to the left-hand side of that equation, we would end up with, right, tau max equals K times tau nominal. Okay. Up to this point, we have an equation, right, that we've used in torsional problems that looks something like this, right? A tau max equals TC over J. Those tau maxes are not the same thing. Right. This tau max, right, is the maximum shear stress at some given torque, at some max radius, and some polar moment of inertia, right? This equation would allow you to calculate, right, this left-hand equation, tau max, would allow you to calculate what's the maximum shear stress out here where we have our maximum diameter, or in here where we have our minimum diameter, right? Does not consider the fact that we have stress concentrations, right? We have amplification of the stress due to having discontinuity, right? In this case, a notch, right? So this tau max here is really like tau max max, right? Tau max max, right? We're going to take our stress, right, our nominal stress, it gives an equation for it, 16 times the torque divided by pi d to the third. That's our nominal stress, which is really TC over J, but they've simplified this based on the fact that C is 1/2 the diameter, so they just plugged all that in, simplified this for just the torque and the diameter. Okay, so we've taken that, which is the shear stress, or tau max, at our small diameter, and now we're going to amplify it by K, so we're going to get the max stress, right? The amplified stress that we're going to see because we have this groove, right? The fill. So this tau nominal is really tau max at our minor diameter. Right? D is minor diameter. Big D is what we'd call our major.
Please try again.
Bummer. But the process is the exact same, right? We need our stress concentration factor. It's on our y-axis. So we need 2 points. In this case, we need a point on our x-axis, and we need the curve with which we're going to use, right? Which is based on our major and minor diameters. In this case, if we had a grooved shaft, we call this a U-groove. These are a lot of times used in what we call pillow blocks or thrust blocks. METs, you guys learned about those? So it's like in a shaft, right? A lot of times shafts, especially with torsional shafts, right? We have rotation going on, high torques. We need to hold that shaft down, right? Or we need to support it. Sometimes we're transmitting that rotation a long distance. And so what we end up doing is we end up putting bearings on it. Well, a lot of times you don't want this shaft to just creep its way down, right? And move horizontally or along the length of the shaft. So you put a U-groove in it, and then you end up encasing that in a bearing, right? So now the bearing keeps that shaft from rotating up and down and wobbling all over the place, but it also keeps it from moving in the longitudinal direction, right? And if you had a drill stem, and we're going to look at like a drill stem, right? And you're trying to twist something and push it in the ground at the same time, right? You can use a U-groove, and that gives you an ability to push on the shaft, right? While something else is rotating it, right? A stepped shaft, that's what this is. A lot of times used in pinion gears, okay? We're gonna go through an example of that just on the next sheet. But these are the two big stress concentration diagrams, right? Whether we have a stepped shaft, we're changing the diameter of our shaft for some reason, okay? Or we need to hold our shaft down or apply a longitudinal load or fix it in the longitudinal direction. So we end up get this U-groove in our shaft, okay? So we're going to go through a couple examples, or just one example here. All right. METs might be more familiar with this, okay, but it might be profiling, right? This is a ring and pinion, right? This is what's found between the rear, okay, if you have a two-wheel drive pickup, okay, in the back you got an axle, right? You got two axles that run from your tires. They go into what we would call a differential, right? So you got these two axles that are in this differential. What ends up happening is we need to drive those axles, right? So they put what's called a ring gear in that differential, right? It's called a big pumpkin or something, right? It's a big void between our rear end, okay, our rear axle, or our rear tires, okay? Well, we need to take that rotation of our tires, right? And we have a drive shaft that's running perpendicular to that, right? So we end up running a pinion gear on this ring gear to take rotation around the ring gear, right? And rotate it the other way around our drive shaft. So we get this pinion gear that drives our drive shaft, or our drive shaft drives the pinion gear, and then we're driving our vehicle's tires, right? And so this would be a stepped shaft, right? We've got a drive shaft that goes on the end of this. It's applying a torque from the engine, right? And that torque then needs to get pushed into this gear, right? There's a gear ratio associated with this. Maybe you've heard someone say, like, I got 410 gears, or 456s, or 512s, or something like that, right? 393s. That's all based on, right, the diameter of this ring gear and the diameters of our pinion gears, okay? And so you have to step this shaft, right? It's going from a larger diameter where this gear's at to smaller diameters as we move. And so then we run an analysis to make sure that if we have an applied torque, so in this case, we have 4,400 pound-inches, okay? That's applied at the end of the shaft, the small diameter of the shaft. And we say that the shear stress in the shaft, moused, I don't know why moused is there, must be limited to 8,000 PSI, okay, when it transmits this torque. And they want us to determine what's the minimum fillet radius needed at the junction between the two portions of the shaft. Okay, what's R? Well, we know stress right? Our shear stress is TC over J, right? This would be our maximum shear stress either out here in the gross radius, right? The major diameter, 3 inches, or the minimum diameter, 1.5. And we have all of that information, right? We have the torque applied, we have the major and minimum diameters, and we have J because we have the diameter. This we would call our, right, this is now our nominal stress. And we know when we're calculating the nominal stress, we're using the minor diameter because we're using the tables in the book or our figures in the book. And we know that that nominal stress times our stress concentration factor gives us our max stress, right? Which in this case, they say that the max stress cannot exceed 8,000 PSI, right? So where does our radius come in? Well, if we look back up here, we have a stepped shaft, right? We're going to want to know our stress concentration factor. Well, that stress concentration factor is a function of our major and minor diameters, but it's also a function of this R over D ratio, right? So if we knew the stress concentration factor, we can work backwards now too, right? In the axial cases, we started at the x-axis, went to a curve, hit the y-axis. Well, we can start at the y-axis, hit a curve, and go down to the x-axis, right? And figure out what type of radius to minor diameter ratio that we need to make sure we limit our stresses, okay? And as you can see, as this R over D ratio gets really, really small, right? If our radius gets really, really small, we're going to move way down here on our x-axis, we're going to get closer to 0. That stress concentration factor goes through the roof, right? So like whenever you're putting a notch in anything, cutting, like changing dimensions, right? Put a radius on it, okay? Put a radius on it. Otherwise you get high susceptibility to cracks that form right at that notch, right? A 90-degree angle. And as you can see here, that stress concentration goes through the roof. And you could nearly double the stresses in that just by doing a very small radius. All right, so we have tau max. We know the nominal stress. We can just start calculating things, right? Tau, we have 4,400 pound-inches. We have a radius, that's the minor diameter over 2, right? We're calculating at the minor diameter because that's what they tell us our nominal stress needs to be calculated at. J is pi over 32 times that diameter to the 4th. We end up with tau nominal equal to 6,639.7 PSI. Well, we know our stress concentration factor. We need that, right? We just decided that that's our way to figure out what our radius is. That's going to be our maximum stress over our nominal stress, or 8,000 PSI over 6639.7 PSI, or we get a factor of 0 or 1.2, right? Well, as we mentioned, right, 2 factors influence K. We have our major diameter over our minimum diameter, right? That denotes what curve we're on. And then finally, our x-axis value is our radius divided by our minor diameter. This is known, right? Our curve is known. That's big D over little d, or 3 over 1.5. Our curve we should be using is 2. So now we can use figure, to find R over D, right? So So we got K is 1.2, D over D is 2, right? So 1.2 to 2. Go here, start at 1.2. We're going to go to the second, or the curve that's associated with. So we're going to go way out here. We'll go down to here, right? So this is our R over D ratio that we want for our problem. In this case, I'm going to guess at 0.238. Right? What does that mean? Well, that means that R equals 0.238 times the small diameter, or we get a radius equal to 0.357 inches. Right? A little less than 3/8 of an inch, right? And that'd be a minimum radius, right? Anything more than that, and our R over D ratio gets larger. If our R over D ratio gets larger, right? We go further and further down this curve, which further reduces our stress concentration factor, which would mean that we're going to stay below that 8,000 psi stress level. Yeah.
How often in like field application would you hit like those curves like on the mark? Like, are you always gonna get like 2 and 2.5, or would you get like an estimate?
It all depends on the like in service, like what the actual element is used for, right? I mean, if you're really stepping down the shaft, then you're going to get higher and higher, right? And this graph is only good to 2.5, right? You could only reduce it by 2.5. So you would go to some other prepackaged solution, or right, you step it even further. And a lot of times, like in the car industry, they're not using these graphs, right? They're modeling it in SolidWorks. You guys have familiarity with that, right? METs do, okay? CETs, I don't know if you guys have used visual analysis, okay? It's a finite element analysis software package, okay? So essentially you take the real world, you break it up into tiny little pieces, and then you use computer analysis software to solve those little pieces, what's going on between each of those pieces. It gives you nice little graphs of showing you like stresses and everything. I mean, that's how the like aeronautical industry, that's how they do a lot of stuff also, okay? This would be if you're like a small fabricator or something like that would be my guess. Any other questions? Nothing? Okay. Man, we are gaining ground. So that is all stress concentrations, and that ends anything you need for the homework that's due at the end of next week, okay? So you guys could just hammer that out, right? I'm sure a lot of you have already started it, right? You're really cranking on it right now, all right? So that's it for stress concentrations. We're going to now step into combined loading. And when I talk about combined loading, we're going to be talking about torsion and axial loads, right? Those are the two load sources that we've talked to this point. But I thought it'd be a good step to just stop here and combine these two load sources, right? Then we're going to actually get into bending, and then we're going to take bending loads, right? Bending stresses, bending forces, and include those at the end of the semester, okay? So we've got axial and we've got torsion. If we look out in the textbook, for some of you guys that are reading along, right? I'm sure all of you have the text on your nightstand. That's what you're looking at on your phone, just scrolling through, reading it at night, right? Right? If we look at the real world, right? Like that pinion gear, for instance. This pinion gear has a worm gear on it, right? And as that worm gear is rotating, that pinion gear not only has torsion on it, but the fact that these gears, right, are radius the way they are, there's actually a thrust on this pinion gear. This pinion gear actually wants to move in and out of our differential. And so we gotta restrain that. So we end up with a bearing on it, right? Then we attach a yoke to it to transfer it to the drive shaft, right? And so the real world is a lot more complicated than just saying, oh, we only have axial load in this system, right? We only have torsion in this shaft, right? We're gonna have torsion, we're gonna have axial forces, we're actually gonna have bending forces also in a lot of cases. So a couple examples I pulled out, okay, to highlight you METs and CETs, right? So let's start by saying this, right? Rarely does torsion or axial forces occur alone in the real world. Right? Gravity is a big one. Right, it's always there. It's relentless. You're not going to get away from that, right? So the second you take a shaft and you put it horizontally, right, just the self-weight of that shaft is going to want to bend it, right, between our pillow blocks or thrust blocks or somewhere where we're supporting our shaft, right? So we're going to get combined loading. We're going to start by looking at axial loads and torsional loads combined. Okay, so for you METs, this is one hell of a propeller, right? It's on a big-ass ship, okay, cargo ship. Well, if we broke this down into somewhat of a free body diagram, we could say that we've got a motor, drives this propeller, right? And that prop, if we spin it one direction, right? If we spin it clockwise in this case where that person is standing, we're gonna wanna push our boat to the left, right? Well, if the propeller is pushing our boat to the left, right, we're gonna have to push on that propeller, right? And so the water is pushing back on this propeller and the propeller is pushing on the water, right? Equal and opposite forces. And so we're gonna end up with an axial force in this shaft, right? And that axial force, then we're gonna have some sort of pillow blocks, thrust blocks that are on that shaft like we talked about. The shaft might have U-grooves in it that holds that shaft to the hull of the boat, right? That allows that axial force to get transmitted into the boat, and then we get a thrust forward, right? Well, in order to get that thrust in the first place, we have to spin this prop. When we spin this prop, well, we're gonna have to there's gonna be resistance to spinning this in water, right? So we're gonna have to induce some sort of torsion into this shaft. So we're gonna have something like that going on, right? We're gonna have an axial force, we're gonna have a torsional force in the shaft. And so we got all of these combined forces adding up in the shaft. And we need to make sure that that shaft doesn't twist off, right? Or if we throw this boat in reverse, right? Now we're gonna be pulling on the shaft. Now we have a tension force in the shaft. We might just pull the shaft apart, right? Wouldn't be a good thing, right? Be hard to do that in the water. So that's for you METs. CETs, okay? This is a picture up in Spanish Peaks, okay? Up in Big Sky. This is a big ass retaining wall that's holding back the entire mountain, okay? I don't know if you guys have driven up there. It's public. Spanish Peaks Resort is a public thing. All the roads in there are public. So you go up there and drive around in there. There's mountain bike trails all around there too, okay? They're open to the public. They tried to gate it off, but they can't because it's public property. So you can go up there and you can drive through this, all right? There's a huge building up there, like 9 stories, huge lodge, brand new. It's like one of the largest buildings in the Northwest, all right? So check it out, all right? Massive. They realized when they first started building it that the building weight was pushing it down the mountain. So what do? Well, they go up there and they drill a bunch of holes, fill them with rebar and concrete, tie back the mountain, okay? So there's a series of these drilled caissons, drilled piers in a ring in this valley between these mountains, okay? That essentially tie back the mountain and keep this building from going down. Right? They perpetually, the engineering company that I used to work for, we had surveyors, they'd go up there once a week, they had a bunch of prisms out on the wall, and they would essentially have a robot total station, and it would just go boom, 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 shoot all the stations on the thing, and they could start mapping how fast or how slow that this mountain, right, was falling down the hill. Okay, so they put millions and millions of dollars into it. Okay, long story short, right, we put a drill in the ground, right, we're gonna have thrust, we're trying to push that drill into the ground while also twisting it, so we get this combined loading of axial and torsion, right? Okay, have a great weekend. We'll see you on Monday.